Hello everyone, this is Math 140, day 12. Our topic is functions. You've already seen some of those issues in the project, and we're going to start right at the beginning. What is a function? So I would picture this as an input which gets put into a black box and then produces output. And because we're dealing with numbers, we will have a one-letter name, which standard would be X. You put that into some kind of a black box, and the output as a standard would be named Y, but it doesn't have to be X and Y. It can be U and V and A and B, whatever. Now, we will oftentimes use a notation where we have a formula for this output, and we write f of x. So we will often write f of x is y. And that means you can substitute for x numbers, and then the formula gives you a value, and that is the y. Example, f of x is x squared minus 1. That's your y, and then you can do f of 5 is 25 minus 1 gives you 24. All right. It doesn't have to be always an equation where the y is all by itself on one side. This could be rewritten in many different ways. For example, you could write x squared minus 1 minus y equal to 0. So you get a relation between x and y, and it's still true for every x, you get one y value, and it gives the same relationship. And generally, if you have just equations, random equations with x and y, and we can always say they define a relation. It's a technical term. It's not relatives, and it's not relationship. It's called relation. Defines a relation between x and y, and such a relation is called a function. If for every legal input value you get exactly one output value y. back to this. This is the case for every input value x. You get one output value y, obviously, and it's still the same. The same thing is true here. So that defines a function. X squared minus 1 minus y equal to 0 defines a function. And x squared minus 1 minus y squared equal to 0 does not define a function. A relation between x and y? Sure, yes. Any equation with x's and y's in them. But not a function. And if you want to drive that point home and nail this down, then we got to give an example. Let's do x equal to 3. So y could be the square root of 8. That makes that equation true. And x equal to 3, y equal to negative square root of 8. That's not nice. Also makes that equation true. So for one and the same x value, you get two different y values, and that's not allowed. That's a frowny face. Right. It's an important connection to geometry that we can graph the points where an equation is true. All points, let's stick with the standard x comma y, where an equation is true. And that works even with relations. We can always plot those points, at least in theory, all the points where an equation is true. And I could make a graph of that second example, which is not a function, but I'll limit myself to the points which I just calculated. Three, y is plus minus square root 8. You have 2 points, which would be 3 comma square root 8, which is a little less than 3. And then three comma the negative square root of 8. So mirror image down here would be both part of the graph of this equation. If I really want to graph this, I should add a couple more. What could we do, for example, if y is 0, then x could be plus minus 1. So we have points like this. Part of the graph. And okay, generally what you'll get is a figure like this. And then it's mirror symmetry like that. So it's not the point here. The point is that this relation does not define a function, or it is not a function. The equation doesn't define a function, and we can tell because we have 2 points with the same x value but different y values. And this has a name, this test has a name, whether a graph defines a function or represents a function. That's called the vertical line test. Graph defines or represents a function exactly if there is no vertical line that hits the graph in 2 different points. Hits is informal language. The technical term is intersects. Intersects. The graph in 2 or more points. And what we just did with those 2 points, 3 comma square root 8, 3 comma negative square root 8, that would be a case of failing this vertical line test, because this vertical line hits the graph in 2 points. And if I go back to my example with x squared minus 1 minus y equal to 0, which of course is just the very first example in disguise, x squared minus 1 is y, that gives me a graph like this. 0.0 comma negative 1 is on the graph, 1 comma 0, negative 1 comma 0 is on the graph. When x is 2, then we get y is 3, x is negative 2, we also get y is 3. And we can guess roughly the shape of the graph. This sort of graph is called a parabola, and we'll learn more about them in the near future. But the point is, for this subject, that no vertical line intersects the graph in 2 or more points. How to tell? Best look at the equation. Whenever an equation is of the form f of x is y, so the y is all by itself on one side and all the rest is the x's on the other side, it clearly defines a function. There's always going to be one single answer for y. Because you can rewrite the equation x squared minus 1 minus y is 0 to be of that form, that equation defines a function. Okay, so very basic object. This is not rocket science. We do need to look a little bit at the one word that has snuck in at some point, that it's true for all legal input values. And a set of all legal input values is called the domain of a function. Let's put that legal in quotes. By default, we take every possible x value where a formula makes sense. Right, f of x was actually a formula, makes sense. If you do that, and you want to be specific about it, explicit, we call that the natural domain. The set of all x values where f of x makes sense is called the natural domain. As an example, one over x minus 1 plus 1 over x minus 2 equal to y. That is a function, or describes a function. What's the natural domain? Whenever I ask a question like this, it's a good idea to pause the video, unless you're sure of the answer. So the natural domain for this is all x values except for 1 and 2, because 1 and 2 would obviously make a denominator equal to 0, and that is not defined. That is illegal as an operation. So that's it. Sometimes Alex will ask you to describe such a natural domain in terms of inequalities. And sometimes they use intervals. And we'll deal with them later. Thursday. Sorry, Tuesday. But maybe one more example where the natural domain is something different. Not every x value is possible. Square root of x plus 3 equal to y. Now the default, behind the default is that we're always dealing with real numbers. In this module, nothing about complex numbers. So this only makes sense when under the square root, there's nothing negative. X plus 3 can't be negative. It has to be greater or equal to 0. There's your inequality. And when does that happen? It happens when x is greater or equal to -3. And we can also write that as an interval. So there's my thing with inequalities, sometimes intervals. Closed interval starting at -3 and going all the way the rest of the number line to the right. This is how you write that. And that 8 lying on its side is the symbol for infinity. What does it mean? It's a question for philosophers, not for mathematicians, really. Mathematicians just work with it. What do we do with it? It just means the entire number line starting at -3 and then off to the right, which, depending if the video is not flipped, is that way for you. All right. So we'll do more examples about inequalities and intervals. You should just be aware that for some functions, the natural domain is not every possible number. And then it's possible to artificially limit the legal input values. And a typical example that always comes to my mind is minimum wage. If wage is your input, the output function is maybe profit because you're working for the man, or revenue or costs or whatever. But if it's wages, then your formula might well make sense for every possible value of x. But because of the minimum wage, there's a law, and that law says x is greater or equal to $7.25 per hour. What the units. Even if your profit would be bigger, if you paid less, you can't. Unless you're waiting tables in a restaurant. Different story. I'm just saying that there's plenty of examples where formulas make sense, but there are outside restrictions that limit the domain of a function. So that's it for functions. On to the next topic.